Hello. In this lesson, we are looking at question 34 of 2020 HSC Physics. Um, a charged particle Q1 is fired midway between oppositely charged plates X and Y, as shown in Figure 1. The voltage between the plates is V volts. So between these two plates we have a voltage difference of capital V volts. The particle strikes plate Y at point P, a horizontal distance S from the edge of the plate. Ignore the effect of gravity. Plate Y is then moved to the position shown in Figure 2 with the voltage between plates remaining the same. So we're doubling the distance between them. An identical particle Q2 is fired into the electric field at the same velocity v as this. Entering the field at the same distance from plate X as Q1. So here we have a distance of d on 2. So here also the distance is d on 2. Compare the work done on Q1 and Q2. We know that the work done on a charge inside a magnetic field is equal to the potential, electric potential difference through which it moves times by the amount of charge. So here our charge is Q1. The voltage difference or the electric potential difference between X and Y is D, which changes in a linear way. So here we have half of that voltage as compared to here. So the voltage difference between this position and this position is V on 2, or half V. So then we said work is the charge times V, and V is half of the capital voltage we have, capital V. So that gives us Q1 V on 2. For Q1, I just used Q because we are talking about the same charges in both cases. So this is Q and this is Q. I just used Q. So we end up with QV on 2. That's how much kinetic energy this charge gains when it goes from this position to this position. Similarly, for this one, it's a bit different. Still released from the same position, but this time the electric potential difference still is V, but this is a quarter of a distance. So in other words, 3/4 of the distance are on this side, 3/4 of the distance of the whole distance is on this side. So that means 3/4 of the voltage also is on this side from here to here. So we have then the amount of change in kinetic energy equal to the charge times the potential difference that it goes through, which is 3/4 of V. And that gives us 3/4 times Q times V. So how do they compare? We can divide this by that and see QV will cancel out, and 3/4 divided by half, which is 2/4, so that becomes basically 1.5 times of that. And the change in kinetic energy. All right, in part B, compare the horizontal distance traveled by Q1 and Q2 in electric field. So we are trying to find S here, and we are trying to find the horizontal distance that this travels here. We can either explain it qualitatively, but I've done it quantitatively, and I'll show you how we can do that. For charge 1, F is equal to ma, because it's accelerating vertically. Okay. This is exactly a projectile motion, but with a different acceleration, and rather than accelerating downwards, it accelerates upwards. Now, F is equal to ma. How much F we have? F is equal to strength of electric field times the charge. So strength of electric field times the charge. How much is electric field? Voltage difference between the plates, which is the capital V, divided by distance d. So times by q. That is the amount of force that this charge experiences as goes from this position to this position. And it is up, vertically up. So to find how much acceleration it has, we divide the force by mass. So that's the force, and it has a mass of m, so VQ divided by m. Then on the other hand, the velocity in y direction is equal to a times t. So when it reaches here, just before hitting this plate, has a velocity in vertical direction, which is vy. So horizontal velocity v is preserved, and it gains vertical velocity, and we call it at that position to be vy, and the vector sum of them is v final, vf. All are lowercase v's. Capital V we are using for the voltage. All right, now we have the acceleration. How much acceleration? It is gaining upwards. And Vy is equal to at, because the initial velocity in vertical direction is 0 here. So Vy will be 0 plus at, or just 80. And then acceleration that we found here, we substitute for this here. So we get capital V times Q divided by md times t. Then putting Vy equal to 80 and Vy is equal to this. T will be equal to md Vy over Vq. So basically what we've done here, we have replaced this Vy with 80, and we have replaced A with Vq on md. So mq Vd mq times Vy equal to T. Basically, this A that we have here, we can replace it with this, and from there we work out the time. That is how we end up with this time. So this time is equal to Vy divided by A, but A itself is that much. So you replace A with this value, and you end up with T equal to. On the other hand, the amount of the work done is equal to change in kinetic energy. That is the work done on the object, on the charge, which we have from the previous part, and the change in kinetic energy is half times m, final kinetic energy, which was Vf, that is the total kinetic energy, the total velocity we have, Vf squared, minus the initial velocity which we had, V squared, Vf squared minus V squared. And from here, we find Vf squared minus V squared to be 2 times Qv divided by m, and that halves cancel out, and we end up with Vf squared minus V squared equal to Qv over m. Just simplified of this, form of this, and making Vf squared minus V squared the subject. On the other hand, Vf squared minus V squared is Vy squared. You can see from here, we have a right angle triangle here, so Vf squared minus Vy squared is equal to V squared. Or Vf squared minus V squared is Vy squared. And Vy squared, Vy becomes square root of Vf squared minus V squared, just square root in this. Now, time is equal to, from here, m times d over vq times v, but times vy, and vy is going to be vf squared minus v squared, which is again in turn is qv on m, but we need to square root it, so we get qv on m. After simplifying, that gives you root m times d over capital VQ. Now your s, the distance is, now we have the time and velocity in x direction horizontal is v, just times them together and you get s. That is the s for the first one. For the second one, again we follow the same procedures. F is VQ divided by 2D because the distance is now 2D. That is Q, that's E, V over 2D. Basically we are using this formula. F is equal to EQ and E is V on 2D. And acceleration is F divided by M. So VQ divided by 2md. So remember that the two charges are identical. So that one also has a mass of m. Again, the same procedure, Vy is equal to 80. This time we are talking about this Vy. Vy equal to 80 and Vy is equal to A is VQ over 2md and times by t. Just replace the A with this one. Then this is the work done, which we found again in the first part. Work done is equal to change in kinetic energy. So that's the change in kinetic energy, half m v final squared minus v squared, and that is equal to Vf squared minus V squared gives you Vy squared using Pythagoras here. So Vf squared minus V squared gives you Vy squared. And Vy squared itself is equal to 3 on 2 Qv divided by m, just making Vy squared the subject from this equation. And then square rooting gives us that. Then that is Vy, and we know Vy is equal to AT, and A is that much. So VQ over 2m times T. And from here you find the value for T, and now the horizontal displacement for that is T, which is that much, times by V. Now we compare the S for the first one with the S for the second one. As you can see, this one is root 6 times of this. So this goes a horizontal distance, which is √6 times the first charge. Thank you for your attention.